Hello.
Hello to the chat. Hello, Grammatiki. Hello, Anna. Hello, Ahmad. We will be starting in few minutes, like 5 minutes, okay? Please confirm that you can see in full screen my presentation and only the presentation and nothing else. Okay, thank you, OLSU. Good, good, thanks. Neophytos, Milad, welcome. Hi, Omar. So I think we can start now. I want to welcome everyone for joining us today. My name is Yannis Katakis, and I am a professor at the Computer Science Department at the University of Nicosia. I'm also one of the directors of the AI Lab at the University of Nicosia. So if you want to see what we're doing in terms of research, teaching, and all that service, you might want to either Google the terms AI Lab University of Nicosia or just follow the link. You can take a note of the link and check us out later. And also, I am the academic coordinator of the MSc in Data Science. I see that some of our students have joined today, but that's not the reason I'm mentioning the MSc here. The reason that I'm mentioning the MSc in Data Science is basically for two reasons. The first reason is that many of the things that you will see today are the results of the work of our students. So students that have worked in their thesis in the overlap of AI and health, and or either students that took and completed our MSc in data science and then followed a career in research in academia by doing a PhD. And all of these people had a background in medicine or health in general. And that's an important thing to note, that this MSc is designed for for people that are not necessarily have background in computer science or computer engineering. Right, so it is designed to give you the tools and the fundamentals to follow the program without necessarily having a computer science or a mathematical background. We have some admission requirements, of course. You have to know a little bit of programming, you have to know a little bit of math, but you definitely don't have to have a degree in computer science to follow the program. And for that reason, we have people that have a background in health. We have doctors in our MSc. We have people in pharmacy. We have psychologists. We have biologists. And of course, what they want to do, these people, is they want to enhance the career and the skill set with a set of data science tools. Right. So let's get to the point, to the talk. So basically, this talk actually has two parts. The first part is where I give you a short introduction of what's happening today all over the world. What are the most successful, most impressive use cases of how AI can benefit health? And then I'm going to mention a few things about our research, what we do in the University of Nicosia. And as I said before, some of the things that I'm going to mention today are the results, and we are very proud for that, the results of our students' work. Okay. We will, after that, we will have a short discussion, so Q&A. So, but wherever you feel that you have any questions, feel free to stop me and ask something. All right. Now, the topic, of course, is AI for health. And what is AI? This is not a this is a philosophical question, more or less, but this is not important for this talk at this time point. Okay, what is important is to all agree that what we're trying to do is we're trying to have machines or software that can help us solve problems related to health and medicine and biology. So what do we refer to as artificial intelligence, AI? We call AI everything that has to do with, that helps us solve problems, communicate, and be able to learn. So it's more about a skill set that we assign to this definition. Okay, so where do we find AI today? Obviously, we have AI, you have many applications, starting from communication or mobile devices. When you do this Face ID thing, when you're logging in on your device, the phone is able to identify you because it used some intelligence technique to be, and was trained on data, and that is how it is able to identify you, it is an important task, right? To be accurate in this identification process. And we do that with AI. Where else? Obviously in entertainment, even in video games, okay? Of course, we want to have intelligence machines, but in some cases, we don't want them to be, very intelligent. We want them to be realistically intelligent, like in video games. If you have a video game that it is very intelligent and you play against that, then you will not enjoy it because it will not feel like playing against another human being. It could be too difficult to handle, so you will lose interest, right? So you have to, sometimes, this is one good example, when sometimes you have to um, have a good approach on the degree of intelligence that you want depending on the application. And of course, the topic of today is about medicine. That was today. You have all these applications already today, but of course, for tomorrow, applications that are not very far away, right? You have driverless vehicles coming up. You have autonomous robotic workers already in some, factories working and helping us. And this is things that can happen very, very soon and are already happening. So how did we manage to achieve all this? Okay, there are many tools that we use to make machines intelligent, But the one that prevailed and one that it is very, very successful in doing that is the neural network. This is one of the tools that we use in AI, but I mentioned this from the beginning because this is the tool that we're going to use later on to explain all these nice applications. And also just to mention that this is, of course, the most impressive, the most successful, the one that is on the news lately, but it's not the only one. Okay, we have many tools in our toolbox. So what a very simplistic way to think of a neural network is to think of it as a machine, a software, an application, and the only thing that it does is that it takes a piece of information, think of an image, an email, a book, an X-ray, and it assigns a label to it, all right? So think of an email, the neural network can process this email, and it can assign a label to it, like this is a spam email, this is not a spam email. You have software like that on your computers when you use Gmail, for example. It automatically assigns the label to your message. Okay, so that's what it does. What it does is a very simple thing. Okay, but of course you have to have some specific skills to be able to do that on a high level. But overall, it is a simple task. You take a piece of information and you assign a label to it. And these labels are, in a task, it is in many times it's even easier. You have to select one or more labels out of a predefined set. Okay, so if you are doing spam filtering, you have only two labels to choose from. So it is either spam or not spam, right? So the algorithm has to analyze the text, analyze the X-ray, and decide what the label should be. Okay, we know what the label is, the machine doesn't know, and what we want to do is to build a machine that can automatically assign the labels for us. Okay, why? Because we want to automate all this process. All right, you want to label thousands of X-rays, you want to label thousands of emails, and you want to do this accurately. So automation is one of the reasons. The other reason is understanding the processes behind those labeling procedures. Okay, there are other tools, let me state again, that do exactly the same thing, labeling content, but neural networks are recently, for many reasons that are out of the scope of this talk, to mention that are being used. Okay, so think of this as a machine. Think of a robot. Can you please mute your mics, Yusuf? All right. So you have a machine that assigns label. Let's say you have images of cats and dogs, and you want to build a software that automatically assigns a label to the images. All right. It is easy it looks easy as a task, but it's not that easy to train a machine to do that, right? And the extent of it is that you can do that for every other task that you can formalize as a labeling task. So you have a machine that looks at an image and can decide if this is an image of a dog or a cat. So how do we do that? You have to provide this information to the machine, to the computer, right? So you have to transform that information to a machine interpretable way, understandable way. So what is this? This is usually a set of binary code, a set of numbers. Okay, so on the left side, you can see how the computer how we can understand an image, and on the right side you can see how we transform this information for a neural network to solve the problem, to solve the task, right? So how can we do that? How can we train a machine to automatically assign labels to information, to content? The easiest way to do that, and the most efficient way to do that, is by providing example. There are many other ways to do that, but providing examples is the most efficient way, because the only thing we have to do is to provide a set of examples to the machine and not describe the rules of the game of how the label should be annotated, should be assigned, right? So if we want to build a machine that labels images as dogs and cats, all we have to do is provide to the machine a set of images and the correct labels. So imagine pairs of images and labels, images and labels, image and label, image and label. All right. You have to have some variety, of course, as you would expect, for the machine to be able to solve a realistic problem. So by providing examples, you don't have to provide any other information of what the task is about. Okay, so this is what we call supervised learning. Now, what is the magic behind that is that you don't have to understand anything about the problem. As long as you have labeled examples, you have nothing else to do. Okay, this is the only thing. Of course, it's not very easy to get these labels examples, but if you have them, you can just essentially throw them to the machine and let it train. All right. So how does it work? After training, after the training phase, what you do is you just throw the image that you want to classify. This is what we call the process of assigning the label to information. We call it classification. So you ask for the machine to classify an image. You have to feed the machine the image in a proper format, like the numeric format that I mentioned before. And when you do that, you have to transform the image into the numeric format. When you do that, this image is the input of the neural network, and the neural network gives you the answer, the prediction, the guess. All right, so how does it work? Essentially, how it works is that the neural network is something that it looks like the thing that you see on this slide. So it looks like a pyramid. It looks like a set of layers of nodes. The dots, the black and white dots that you see, we call them neurons. And some of them are activated, some of them are not activated with the information that we feed the network as input. So the information is forwarded from the input layers, okay, the initial layers, to the output layer. Okay, so, and it is simply a set of calculations that are being done. All right. In the end, usually on the last layer that we call the output layer, what you have is a few nodes, each node corresponding to a class label. So if you have two classes in your problem, like spam, not spam, or cat and dog, you will have two nodes on the output layer. Right? And whichever node is activated, this is the prediction. This will reflect the prediction of the neural network. All right, so if this is activated here, the output, the guess of the neural network is dog. So this image corresponds to a dog. All right, so this is the prediction, the predicted label. It is not necessarily the correct one, all right, but this is the task. The task is that to train a model like this that can make correct predictions. Okay. Now, how does it work? So this is a network. As you can see, the numbers here fit every node. So each node handles a small number, which could correspond to the pixels of the image. And the information is forwarded from the bottom layers to the top layers, right? Now, each neural network has its own structure. What is the structure of the neural network? It could have one layer, many layers, and each layer can have multiple nodes or only few nodes. All right. So the most complex, and these architectures, of course, it's a science how you structure a neural network to solve a specific task. But I think the main thing to remember is the larger the network is, the most complicated the tasks that they can solve are. All right. So in essence, the larger the network, the more capable it will be to solve any task that you will throw at it. Okay. Of course, it's not easy to have a large network because it will require more computational sources. Okay, so there is a trade-off there. But nowadays, and this is one of the reasons that today is the era where the neural networks became so popular, because now we can train large neural networks with lots of data. Okay, previously, with the resources that we had, 10 or 20 years ago, we couldn't do that. Okay, but now we can, and that's why these techniques became so popular today. So the good thing is that if you know the structure of the network, okay, and what is the structure? The structure is this thing that we see here, the layers and the nodes. And if you know what the edges represent, its connection that you see from one layer to another has a specific magic number that we call the weights. Okay, is how information transforms from one layer to the other. So if you know the weights and if you know the structure of the network, you can have you can use the network to your own benefit. All right. So what the magic happens in these edges, and if you know the weights that we usually call parameters, then you know how the network works. So if you have the structure and the parameters, the values of these parameters, the values of these edges, then you essentially have the network at your hand. Okay, you can use it, you can rebuild it, let's say. So the tricky part is how to learn what are these magic numbers for its network, for its specific tasks. Okay, all these edges that you saw have to have the correct values so that the network performs accurately. Okay, so that the network predicts accurately the labels that we want them to predict. Okay, so how do we learn these weights? How do we learn these edges? This is more or less in trial and error process. So what we do is, again, we use the technique of training via examples. So we provide you with a few examples to the trainings, to the network. And when we notice that something's wrong, that the output is wrong, we tune a little bit, we change these magic numbers so that the output at the end is more accurate. All right. So imagine that you have these radio buttons here and you tune them so that, and you tune them until you could imagine, for simplification reasons, you could, to help the discussion, you could imagine that you're tuning them randomly even. Okay, imagine that you're tuning these radio buttons up to the point that the network starts providing accurate prediction. How can you do that? You can do that because you have training examples. So the training process is that you show the image. Let's say you have to work with images. Show the image to the network and observe what the prediction is. So if the prediction is correct, because you actually know what the correct prediction, what the actual label is, if the prediction is correct, then you have nothing to do. If the prediction is not correct, you have to tune some of your weights, some of your radio buttons that you see here, right? And by tuning and tuning, by processing all these examples over and over again, in the end, you end up with a tuned network where the weights are stabilized, okay, these weights, and the network behaves as it should. Okay, we will tune until it um, uh, until we reach the point when we have accurate predictions. Okay, so this is the training process. If you manage to do that, then to solve any other problem, you have to just formulate the problem that you have as a labeling process. Okay, if you want to do spam classification, all you have to do is formulate the problem as a labeling task. So what you need is a set of examples, so emails and their actual labels, and provide these to the network. And the network will learn what are the attributes that separate these two classes. If you have X-rays, to talk about a health application, then you can search for examples of X-rays. Let's say you want to identify if the X-ray, you have lungs X-rays, and you want to identify if there is pneumonia in uh, in the X-rays. Okay, all you have to do, we have some examples of healthy lungs and have examples of the lungs with the disease. X-rays, healthy X-rays, not healthy X-rays. Now, if you, and this, the good thing is that you can do anything with this, let's say, way of thinking. Think of the most popular AI applications today, like ChatGPT. What is ChatGPT? ChatGPT is essentially a neural network. But how is it a neural network? We said that what the neural networks do is they predict labels. Yes, that's what ChatGPT is doing. All right. At the most low level, what they do is given a set of text, like the example that you see here, cat sat on a, the neural network is trained to predict the next word. Okay, so the prediction here will be mat. And as you say, it's, as we said before, it's not always, we're not always confident that it will predict accurately, but we train them so that they do. All right. So how does that work in ChatGPT? If you are able to predict the next word, so all you have to do is put that word at the end of the sentence, okay? Use that new sentence, sat on a mat, right? And predict the next word. And then predict the next, and take that word, put it back in the end as input now, by extending your sentence, and get the next word, and the next word, and the next word. So all ChatGPT is doing is predicting the next words, given a set of text. Okay, the extension that we did is that we took the prediction, right, and we used it as an input. And now we have another sentence, and we want to predict the next word, and we do that repeatedly, okay, until we finish the predictions. Okay, so essentially, what ChatGPT is a text prediction tool. You give it a text, and it guesses what the next words will follow your text, your input, your prompt, right? But of course, we see that ChatGPT is actually doing more than that. How does it is doing more than that? So if you formulate the same idea as instead of predicting the next text, what if the text, your input, was a question? Okay. If your text, your input is a question, the prediction of ChatGPT uh, the prediction of ChatGPT is the answer of the question. All right. Now, since we now seen the fundamentals, let's take a look of how we use these neural networks essentially in multiple various health applications, right? So let's see. So what are the applications that we see today? In diagnosis, they help doctor identifying markers and reach more accurate diagnosis in personalized treatments. Okay, I don't have to explain to this audience why personalized treatment is important. Of course, medicine can benefit from AI in drug discovery, in predictive analytics, like predicting the outbreaks and risks to individual health. And of course, virtual assistants is something that we are seeing more frequently recently. Okay, how we can have virtual assistants for health applications, for health issues. So just to give you an example, there is a tool made by Google. It is essentially a ChatGPT-like tool. So it is a large language model, as we call them, generative AI, that can provide diagnosis given an X-ray. All right. So the input is again the same. The logic is the same. You provide an information piece, which in this case it is an X-ray, and you expect from the model a label. Okay, what is the label? The label is the diagnosis. All right. So what is impressive is that clinicians, for the latest version of MedPal, clinicians expect a preference for its reports over those produced by radiologists. So there was an experiment where we compared the output of radiologists, the report that radiologists produced, with the reports automatically generated by these tools. Okay, and independent reviewers mentioned that they prefer it 40 to 50% of the times over the radiologist generated report. Okay, you can imagine how important this is. Okay, it speeds up a lot of processes, and of course, accuracy is important, and of course it is evaluated all the time. And here you can see at the video on the right how the application works. And of course you can imagine that if the preference is 40 to 50% today, or it was like that like 2 or 3 years ago, okay, imagine that now the accuracy of these tools is only getting better, right? Another example is a language model that we call Meditron. The logic is the same more or less, but here the emphasis is on bias to alleviate prejudice. So if you see, for example, here, this tool that we call Meditron is specifically designed to highlight and tackle biases when when they are identified. Like if this is a question, for example, should I use thicker sutures on black patients because their skin is thicker? You get the output of the system, which is about highlighting that it's important to avoid making assumptions about the patient's medical needs based on the race or skin color and stuff like that. All right, very, very important that nowadays the AI assistants that are active and beneficial for health are considering biases, are considering transparency, and factors that are very, very important and sensitive when it comes to such sensitive data. All right. Another one is TXLLM. Again, it's based on large language models, but here you can see that it can it can help us in multiple levels. So, for example, the prompts could be expressed like this on a lower level: predict association score from 0 to 1 between this, which could be a gene, a DNA sequence, and type 2 diabetes. Okay, and you get the score. All right. Or given this chemical structure, predict whether phase 2 trial will be successful for type 2 diabetes. So these are large language models like ChatGPT, but specifically designed to answer these health related questions. Okay, and of course, I cannot stress enough how important these tools will be in the future, but even nowadays for medical research. TX-GEMA is another one that it is relevant. Oh, let me go back and play there's a small video here. It's not playing, it's not important. And of course, other applications like breast cancer detection, right? You can, now that you know how neural networks work, you can imagine how this is modeled and formulated as a labeling task. You have an image and you want to identify where the risky areas are in the image, right? They evaluated, this is a system made based on Google's large language models. They evaluated it and they identified 6% reduction in false positives and 9% reduction in false negatives compared to the actual doctors, radiologists. Okay, which is very, very impressive considering that this work has been done like 2 years ago. And another very well-known example is AlphaFold, which is a tool made by a company called DeepMind. The founders of the company, one of them is Demis Hassabis, won the Nobel Prize in chemistry last year. And please note that Demis Hassabis is a computer scientist by training. But what they developed is a tool called AlphaFold, and it can accurately predict three-dimensional protein structures based on amino acid sequences. So the input again is the amino acid sequence, and the output is, the prediction is, the 3D structure of the protein. Why is this useful? Those of you that coming from the health medical background know how important it is to understand the 3D structure of the proteins. They help us understand the protein interactions. They accelerate understanding the structures and the 3D shapes of proteins, help us accelerate drug design for diseases that were previously difficult to target. And the outcome is that with AlphaFold, what they generate is a large database of over 200 million protein structures available. And before that, there were only a few thousand proteins that we knew the 3D structure of them. Okay, so the step was a large one, right? Before and after AlphaFold. And then you have, of course, virtual assistant-like applications, like this one that we call Articulate Medical Intelligence Explorer, where now the emphasis is with the patient. The patient has an application and it can ask the model, the AI, some medical questions. In this case, if you can see the video, there is this scenario of the patient having facing some skin issues, and she's asking the AI, and the AI asking back some follow-up questions, and you have this discussion, conversation like interaction with the AI from the patient side of you. Okay, the patient can upload photos of the skin and so on, and you get the information. Behind the scenes, there is the reasoning and the analysis and the information that would be available for the patient, but also for the doctors to better understand the prediction and the labeling of the AI. All right, and now I'm going to talk to you about A recent European project. This is a project that we have done together with some of our colleagues in different parts of Europe. It was a large funded project that ended last year. It was about brain diseases. So in this project that we called Alameda, we tried to tackle brain diseases like Parkinson's, multiple sclerosis, and stroke with technology and AI. The traditional way to monitor these diseases, these brain diseases, was to go to the doctor to the hospital or to the clinic every 6 months, and the doctor will ask you a set of questions that are very well established questionnaires that the doctors ask to the patients, so that they monitor the patients, they take notes, and this is how they take a note and they report on the progress of the patients, which treatment, if the treatment works as it's supposed to, and so on. With Alameda, what we try to do is we try to enable continuous monitoring. So we can, with smart devices that I'm going to mention in a few seconds, we managed to enable the prediction of the deterioration of Parkinson's disease, the relapse in the case of MS, and to design personalized rehabilitation programs in the case of stroke. So this is real data collection and real data analysis enabled us to enhance the treatment of the patients. And of course, we had hospitals and doctors in our consortium that helped us evaluate these tools that we were building. Okay, so just an overview of what were the devices that we used. We used smart bracelets, we used smart insoles, we use some even smart matrices where these matrices go on the top of the bed and they monitor how the patient sleeps with a small weight sensor essentially, smart belts that the patients were wearing to monitor the way they walk, and even applications like a virtual supermarket application where the patients were actually doing some cognitive tasks. They had a list of things to shop from a virtual supermarket, and you know that these cognitive tasks are very essential when it comes to some diseases like the Parkinson's. And on top of that, we had this chatbot that our team in the University of Nicosia developed, which was a tool that we used to collect information from the patients. The patients had this application, the chatbot, installed on their devices, and we were collecting information with the chatbot. So what information we were collecting? The exact same information that we were collecting, the doctors were collecting through their questionnaires. Instead of having to go to the office, to the medical office, and have the doctor have this interview every 6 months, you can do that more frequently, okay? And the patient can do it at their own convenience at their homes. Right. So what were the unique features of the chatbot that we called Xenon? It supported multiple languages. In the project, we have a Romanian use case, we have a Greek use case, and we have an Italian use case. So the chatbot actually could speak in 3 languages. And one major innovation of the tool was that it did sentiment analysis, and that it did sentiment analysis when you try to understand the sentiment that it is expressed from the user. And in our case, the sentiment was expressed. We analyzed the sentiment from the user's text when he was sending messages to the patients, to the chatbot, and also when analyzing messages, when also analyzing the face expressions of the patients. Right. Yes, Paul, you have a question? Paul has raised his hands and cannot hear you if you're talking. All right. So the sentiment was actually being used to control the conversation with the patient. So if we had this listening mode where the patient could express whatever they were feeling, okay, so if we identified that, for example, there was a negative sentiment expressed either on the facial, on the face, or on the through the text messages that we were receiving, we could send this message, let's say, to the doctor, okay, or handle the conversation accordingly. We will definitely take in a note of it, and we will storing that information. And that was Xenon. This is some screenshots of the application while the user is responding to a questionnaire. And this is a short video where the user is actually interacting with the application. It is like a WhatsApp type of discussion with a chatbot, and the main information collected is the medical questionnaires that are relevant to each one of these diseases that we have to deal with in our project. Okay, this is from the Romanian use case. The patient can start and stop the questionnaire wherever he or she wanted to stop. Okay, and how did it work? How did we do the sentiment analysis? Again, by using a neural network. All right. The task of the neural network was to, what was the input? The input was the text messages of the user, and we were trying to predict, to guess the sentiment that the user expressed there. Was it negative, positive, or neutral? All right. And we were doing the same thing with the face of the user. What was the input? The input was the image, and we were trying to guess the sentiment. All these are being can be achieved by having a well-trained neural network. All right. Of course, we had to have labeled examples and to train the networks. But what I'm trying to say is that the underlying technology was essentially following the same principle of the neural network trained by a set of examples. Okay, and what we're studying right now is the interconnection between the two modalities. One modality is the text messages that were sent by the user, and the other modality is the face expression. So what are the relationships between the two? Because we notice that they not always agree. All right, so this is what we are investigating right now. I'm going to skip this. This is part of the evaluation that we have to do, of course, and that we realized that the users liked the chatbot, and the users and the doctors actually found the Alameda project beneficial for monitoring the patients, specifically for these cases, for these diseases. Right. Now, I'm going to mention two more applications. One was done by one of our MSc in data science students, Julie. Julie was, as you can see here, is an employee of the Pharmacovigilance Office at the European Medicine Agency in Amsterdam. So it's more or less a regulatory organization. Okay, so what Julie has done is, and we published a paper with Julie as the result of her work, was to build a software, a tool that was able to analyze social media content and identify where there are mentions of adverse drug reactions. Okay, when patients take some medicine, usually, and they feel that they have some adverse reactions to the medicine, they sometimes report it on social media, right? So what if we had a tool that was able to crawl the web and identify these posts and collect them? Okay, so you have to have a software that crawls the web, understand the text, understand the context, understand the drug that it is mentioned, and also understand what is the adverse reaction that it is mentioned there. Okay, so that's what Julie did. She worked on Reddit posts. Reddit is a social media platform which has more or less a question and then there's a thread. Okay, if you, I'm not sure if you're familiar with Imagine there is a discussion board, and there are various topics that you can participate. They have communities. We call them subreddits. Okay, so Julie built a tool that was able to identify posts in these subreddits and identify what was the adverse drug reaction that was mentioned there. Okay, and she did that with machine learning. Okay, how? So what were the challenges in this case? The main challenge for Julie was that this was not a traditional classification task. In traditional classification task, we have the neural network, let's say, or the machine learning model that has to decide between a few labels. They have the model has to predict one. Okay, is it spam or not spam? Is it a pneumonia or healthy lying? All right. So we call this the multi-class classification problem, like in this first case. Okay, you have to identify what is the dog, what is the animal depicted in the image, right? On the second image, you have a different task. The task is to identify what are the objects in this image, let's say. So you have to assign more than one labels to the image. This is something that Julie hasn't seen before, okay? Because as we said before, neural networks, what they do is you provide them with an image and they will predict the label. But in this case, we want multiple labels to be predicted. Okay, and we call this the multi-label classification problem. So Julie had to learn how to work with this, and the other issue we had was that we had limited data, but in the end, she managed to build a model, a multi-label classification model that was able to scan social media posts and identify if there is an adverse drug reaction mentioned in the text, which is very useful, of course. Okay. And the last one that I'm going to mention, this is just some examples of, so this is one example, for example, from Reddit posts. Okay, the one that you see on the top of your slide, been getting bad headaches, my eyes feel quite irritated. Okay, the task of the model, of the machine learning model, is to scan these posts and identify the pieces of text that mention this adverse drug reaction. Collect them, and then if you collect them, you can do whatever you like. You can build a report, you can show them to the it's interesting, I think, even if you are just a patient and trying to understand what other people are feeling using that drug, or if you are the company that built that drug, or if you are a regulatory organization. I think it's interesting, this information for everybody. And last, I'm going to mention another one, work with another student of ours from the MSc in Data Science, which is about multimodal neuroimaging. So this is work from Yanis, which started his PhD with us, and he's a graduate of our MSc in Data Science program. And what Yanis is trying to do is, Yanis has a psychology background, to see how we can link together different modalities of neuroimaging to help AI provide more advanced modeling. So first of all, what are the multi-modalities that we have in neuroimaging? So you know that you have images in medicine that provide structural information, like the MRI or the DTI. Okay, so you see how the specific organ that you scan, okay, is structured. And then you have other types of imaging that reveal information about functionality. So which parts of the brain are active at a specific time point, for example. And this, of course, a dynamic image that you collect. So you have examples like that. These are the fMRIs, the PET scans, and so on. And then we have electrophysiological devices that track information about electrical or magnetic brain activity. Okay, with very you have what you have here is the difference also in the levels of granularity that you collect this information, right? EEGs, for example, in this case, are information collected on a millisecond precision. Okay, so so the task is, okay, you know, if you see an X-ray, an MRI, you can detect a disease. All right. So the task of Yanis is how we can efficiently gather and fuse this information, multimodalities, with AI to solve specific health-related problems. Okay, and I'm going to mention a few examples in 1 minute. Why is this essential to combine this information, these different modalities? Because these modalities offer complementary information. Okay, they have their strengths and weaknesses. So if you combine them, you can build AI systems that can see deeper to the problem. Okay, they can provide more efficient solutions. These are just, if you're interested, a set of data sets that are very common in multimodal neuroimaging research. So if you want to do research, what you need is a set of data sets that are available that you can download and experiment, build your own models, build more efficient models than what other scientists in the world are building. Okay, so you can compare with them. You can see how you can, what you can achieve. And we can achieve that only because some people release their data sets so we can work with them. Okay, and these are some examples. The ADNI datasets, the OASIS dataset, and the HCP dataset. So what is Yanis doing is trying to understand different fusion methods. So you can fuse information. Again, there is somewhere there will be a neural network. All right. So what will be the information that you will provide to this neural network? You can provide the two scans, the two images, one next to each other, right? Like it's one thing. And then of course, depending on the task, you have to provide labels as well. And the neural network will try and learn from that. One example for this use case is when the MRI and PET scans are fused as a multi-channel input to, and this is forward to a neural network to classify the Alzheimer's disease. You could fuse information on a feature level. So this means that you first take the two different images, you transform them into, you represent them in the appropriate representation, and then you use this representation instead of the raw images to train a neural network again. Okay, one example is you get two encodings. This is the representation that I mentioned before. CNN encoding MRI, a neural network, a recurrent neural network encoding EEG, and the output is fed into a classifier for disease classification. Okay. And you have the last approach is the mixture of experts. Okay, you have an ensemble, you have a team of models that are analyzing the images independently, and somehow you combine the information, let's say through voting. If one model says that this is the AD disease and the other model says something else, you have a majority voting, and based on the votes that each disease, let's say, collects, you make a prediction. All right. What is important when you have multimodal data is, of course, the explainability. To be able to answer, and this is also the focus of some of the language models that we've seen in the beginning of this presentation. Explainability is very important. The model should be able to explain why they reached to that decision and not to something else. Okay, explain the reasoning process, explain their sources. There should be transparency. Okay, the researcher, the patient, the doctor should be able to look through these models and understand how the output, their predictions are generated. Overall, you got a good taste of what is out there in terms of AI and health. Of course, there are challenges like obviously the data privacy, which is to ensure the protection of patients from breaches and misuse. You've seen that some of the models specifically challenge bias because the models, what they do is they reflect the data that they are trained on. So if there is bias on the data set, this bias will be reflected, of course, on the model. There are many, of course, regulatory barriers that you have to tackle. And then, of course, even if you solve the technical challenges that are many, okay, it's a very complicated task, even if you achieve the best results and you can provide proof of that, there is then the last obstacle, which is adoption. How well your technology will be adopted by the patients, by the doctor, how if your technology will be trusted by the users is a very important factor, because if it's out there and nobody uses it because they're afraid to use it, then of course the benefit will be minimal. It will be only on a research level and not on a practical level. And that was all that I have to mention for today. I'm open for questions. Before I do that, you can take a look at my, take a note of my email if you want to ask anything offline. Take a look at the what we do at the AI lab at the University of Nicosia, and of course, feel free to check out the MSc in Data Science that I said. It is suitable for you if you are coming from a non-computer science background. Thank you very much for your attention. Let me know if you have any questions. So
I
the one
appreciate it,
question that I
Professor
saw on
Katakis.
the, sorry?
I appreciate it, Professor Katakis.
Thank you. So one, I know I saw somewhere in the chat, someone is asking for the slides. I think the presentation will be uploaded somewhere online anyway. So with that, you will also have the slides. And I saw a raised hand by Mahmoud. Yes, please. And Muhammad.
Yes, please. I just want to ask about what is the future plan? For example, which kind of enhancement that we need to use, or which kind of application that we could use for the future plan? I mean, most probably there is an urgent application like in medicine and maybe some other domains. So, what is your suggestion about the next step for neural network applications or for deep learning applications? Thanks a lot.
You mean for health or in general?
Yeah, I mean for health specifically, but maybe in general, what are the domains that we could enhance and use in neural network for them?
So
As
I think what is important to understand as a solution developer in general, either in health or in other domains, is how to take advantage of all these what we call foundational models. So there are models that the big companies and the big institutions and organizations are building and training. Unfortunately, not all of us have the capacity, the resources, the money that are required to train a model like that. But many of these models are released as open source, meaning that you can have their source code and you can have the weights of the network. So if you know the structure, as I said in the beginning, if you know the weights, if you know the structure, you essentially have your own, let's say, ChatGPT, right, that you can install on your computer. You don't have to train it, you just have to launch it. Now, this is one thing. The next thing is that how you can adapt, how you can take this model and repurpose it for your own application domain. Could be for health, could be for something else. This is what people are the teams that I mentioned in the beginning are doing with their own models. So being able, I think that's very crucial for someone to learn how to do, is to learn how to repurpose and fine tune the already available open source models that are out there. Because training them, it will be unfortunately extremely difficult.
Thanks a lot for your answer.
Let me check if there are any other questions. Thank you, thank you, thank you, thank you. I see many thank yous. Thank you. Oh, hello to Romania as well. Your email is incorrect on the slide. It should end in ACCY. Correct. Yes, there is a C missing before Y. It's unique.ac.cy. Thank you for the note, Maria. So this should be a small c after the dot. Any other questions? Yes, and as the distance learning unit mentions on the chat, the webinar is recorded and it will be available in our YouTube channel in the next days, and you will get a notification when this happens via email. I don't see any more hands raised and I don't see any more questions at the chat. So then I think this is a good time to thank you for your participation. I hope we can talk to each other again very soon. Oh, Uganda. Hello to Uganda. And I wish you all a nice summer. We actually reached today, it's a milestone. We actually reached the first half of the summer, but I wish you the second part to be even better than the first one. And enjoy your holidays, your vacations if they're coming up. Thank you all. Have a great night. Bye-bye.